Did this one? Did I? I'm sure this is where I left off. So 65% of adult Americans are in favor of the death penalty for individuals convicted of murder. In a random sample of 15 adult Americans, we want to find these probabilities. And I said use the table, but I'm probably going to talk about both ways, how to do it by hand and by the table. Just because the table, we are pretty limited. You'll notice I only have certain n values. I give you 2 through 10, or sorry, 2 through 12, and then 15 and 20. So if your n is like an 18, you can't use the table. It's also only certain probabilities up at the top. So if I said like 11%, you can't use the table. So we need to make sure we know both ways. What does this 65 represent? That's the probability that they are in favor of it. So that's my P. What's the 15? N. All right, so for exactly 10, let's talk about, I'll do it by hand first and then look at the table. So if you're looking at your formula sheet, this is a binomial because either they are in favor or they aren't. There's no third option, so only 2 outcomes. Everybody has the same probability, so they're all independent. We only have a set number of trials, so this is binomial. So when you look at your formula sheet under Chapter 6, the third bullet tells us how to find this probability. So n choose x. So my n is 15. Choose, what is my x value here? 10. And then it says p, which we said p was 0.65, to the x power. So that would be to the 10th. And 1 minus p, what is 1 minus 0.65? To the n minus x. So 15 minus 10 is 5. Basically, if 10 of them say they are in favor, that leaves 5 of them to say they are not in favor. All right, and then remember when we did this on our calculator, you have to do your parentheses. You type the 15, then how do we get the choose function? Right, math over to probability, and it's the third one, NCR. So 15 choose 10, 0.65 to the 10th, 0.35 to the 5th. And so we get 0.2123. Let's confirm this with the table. So on the table, first we have to find our n. N is 15, so that's the back page. P is 0.65, so we're looking at that column. And we want to go down to when x is 10. And it also says 0.2123. Does everybody know how to read it on the table? So n is our total number, then we have the probability, and then that's the column. You get it?
I couldn't even get it on to say. This was so big. Yeah, but then she went and adjusted. It was all kinds of she was like, see if you like it.
Did anybody else need help finding that on your table?
And so then I started moving.
Part B, I want to strictly do from the table. I did ask that you guys show me some kind of work to justify your answer rather than just writing down a final answer.
Can I get my stuff out of the season?
That way, if you just type something in your calculator wrong, you aren't losing all the points on the question. So if you're doing it by hand, write out this statement so I know what you put in your calculator. No more than 6. So that means, what do I have to do? It could be 0, or 1, or 2, or 3, or 4, or 5, or 6. So we have to add up all of those values from our table. Okay, so you're going to your 0.65, your n equals 15. And we see at 0 and 1, it has the 0, 0, 0 plus. That means it's a small positive number. For our persist, it's just 0. So we're going to add up the 2, 3, 4, 5, and 6. And this is when the table really saves you a lot of time, when you have multiple things you have to calculate. We should get 0.0423. Is that okay with everyone? The last thing that I want to talk about in general, and we're not going to use this so much right now, it's going to come up more in a later chapter, but since we're talking about the binomial, it's a good time to go ahead and mention it. If n times p times 1 minus p is greater than 10, then when we draw the graph, it's actually going to turn out to be bell-shaped. Okay, maybe not a perfect bell, but approximately. And that will be something that we use a lot more in like chapters 8, 9, and we'll mention it again then. But if those are greater than 10, we'll have a bell-shaped rule, which means then if it's bell-shaped, we could use the empirical rule, right? And the empirical rule, remember, it's on your formula sheet, tells you if your data is bell-shaped, it tells you what % of your data falls within each standard deviation. So I'm just going to do one problem like this. I think I only put one on the homework, just kind of touching on this. So according to Experian Automotive, 35% of all car owning households have 3 or more cars. We used this scenario yesterday. We have a sample of 400 car owning households and found that 162 had 3 or more cars. Is this result unusual? And so we could actually do this a couple different ways. The 35%, what is that? That's the p-value. What's my 400? N is 400. And what's the 162? That's my x. So if I wanted to decide if this is unusual, what makes something unusual? If the probability is less than 5%. Is this one that I could use my table for? No. My table, my n only goes up to 20, so I would definitely have to do it by hand. So if I wanted to calculate this probability and choose x, so my n is 400, I'm going to choose 162. P to the x, so 0.35 to the 162. 1 minus p, so 1 minus 0.35 to the n minus x, 400 minus 162. Let's try that calculation. What happens? It says overflow. Probably not an error you've ever seen before. Basically means the numbers are so big our calculator can't find it for us. So, that is unfortunate, okay? But one thing we could try. What's n times p times 1 minus p here? So my n is 400 times my p is 0.35 times 1 minus p, 0.65. What do we get? And I get 91. That's bigger than 10, which means this data is bell-shaped. And we could use the empirical rule. Okay, so look back on your formula sheet at your empirical rule. This is not something that I would expect you guys to do on your own right now. This is just kind of a good conversation for us to have. Empirical rule is talking about how far you are within one standard deviation of the mean, right? So if I'm going to do that, I need to know what the mean and standard deviation are for this data. Now that we can do. We had a formula yesterday. This is binomial. And so we said the mean is just n times p from our formula sheet. So 400 times 0.35 is 140. Standard deviation is the square root of n times p times 1 minus p. So if we had that, when we talk about the empirical rule, oh, that's really not a very good bell curve, is it? The mean was the center. How did you get the first standard deviation? Okay. So 140 plus this. Let's just use approximately 9.5 to keep the calculations a little more simple. Is 149.5. And then you also have to subtract it. So that's 130.5. Okay, that's within one standard deviation. So according to the empirical rule, what percent of our data has to fall within that window? Okay. We are still talking about a 162, so I'm not there yet. So for another standard deviation, you just add and subtract it again. So if I add my 9.5 again, I get 159, and on this end I get So what percent of the data has to fall in here? If you're looking at your empirical rule, it said 95% of the data is between this and this. So that means 2.5% is here and 2.5% is here, right? 162 would put us in this window. This whole thing only accounts for 2.5%. So the chance of it being 162 has to be smaller than 2.5%, right? Yeah. What does it take to be unusual? Under 5. So my question was not even the probability, just is this unusual? I know that it's going to be less than 2.5%, so that would make it unusual. All right, I know that was a way more abstract calculation. I'm just kind of trying to show you how some things relate, how we can take this back to the empirical rule that we had before. So this is not something that I expect you to do on your own right now, Okay, we're just talking about how to connect the binomial to what we had before. What I want to do now is take just a little bit of time and go back and review some of the things from chapter 6. So we'll do a few examples like that, and then you have time to work on your own for the rest of the hour on that homework from yesterday. So, this first question. A college is trying to determine the typical age of its professors. A survey is given to all professors asking their age. What is the variable? What variable am I worried about? Age. Is age going to be discrete or continuous? Continuous. It would matter, you know, how I ask the question too. If I said specifically I wanted your age in years, that would be discrete, but technically age is continuous, right? Because you can give it in years, or years and months, or years and months and days, or you could add in hours, or minutes, or seconds, so technically it is continuous. What would be my possible values? Anything, what? Anything greater than or equal to 0. Now in practicality, are you going to have a college professor with an age of 0? No, but is there a rule that says how old a college professor has to be? Not really, so we can't really, for our purposes, this is sufficient. Okay. Let's talk about probability distributions. So here is a function. What do I mean when I say make a probability distribution? We make the chart. We list the x and the p of x. And what x's do I need?
1, 2, 3.
And how am I going to get the probability for each of these? Plug it into my formula. So if I put in a 1, I get 4 over 10, 0.4. If I put it in 2, I get 3 over 10, or 0.3. If I put in a 3, I get 2 over 10, so 0.2. If I put in a 4, I get 1 over 10, which is 0.1. How do you know this is a probability distribution? They're all between 0 and 1, and they add up to 1. Okay, we've talked about finding the mean and standard deviation of these. We mostly use the calculator, but we could do it by hand. Let's practice the by hand. So if you look at your formula sheet, I don't know what I did with mine. So under your probability distribution, so at the beginning of chapter 6, it is our, what do you need?
I got some components.
So your mean, it tells us we have to add up the x times p of x's. So we could quickly just add another column, x times p of x. So 1 times 0.4 is 0.4. 2 times 0.3 is 0.6. 3 times 0.2 is 0.6. 4 times 0.1 is 0.4. So the mean, we just add those up. And we get 2. All right, how do we find standard deviation? So that's really just taking this column and multiplying x with it again. So 1 times 0.4 is 0.4. If I take this, I get 1.2. 3 times 0.6 would be 1.8. 1.6. Does everyone know how I got those numbers? So if we are looking at the standard deviation, second bullet, it tells us it's the sum of the x squared p of x's. So if you add all those up, what do we get? sum of those minus the mean squared. So my mean was 2. So I have the square root of 5 minus 2 squared. So we just get 1. I also asked for variance on here. I don't have a bubble for variance, but do you remember if you look back in chapter 3, if we have standard deviation, that was sigma, what's population variance? Sigma squared. So it's just your standard deviation squared. So that's 1. Is that okay with everybody? I just wanted to also refresh how to find the mean and standard deviation on your calculator. So I have this one. What did we do here? So we go to Stat, Edit. You want to list your x's in L1 and your probabilities in L2. So then we go into Stat, Calculate, one variable statistics. Your list should be L1. Frequency list should be L2. Your calculator may already have that because that's probably the last thing we calculated in here. But list L1, frequency list L2, and then hit enter. So our mean is the X bar. So 1.2517. Standard deviation is the sigma 0.9693. That was kind of the older stuff. The rest of it is over this section. Do you want me to keep working that, or do you want to save those 3 for the beginning of class tomorrow? I'll let you guys work on homework right now. Would that be okay? So I've reviewed the older stuff.